Hi, my name is Kaajal and I, along with Casey Tokita, am leading the needleless EpiPen redesign project. We are addressing the fundamental problem of the EpiPen. Currently, there are several drawbacks about the EpiPen that have been seen in FDA research and involving talking to kids who have severe allergies as they go into adulthood and dealing with the needle and dealing with the trauma that comes with it. And from that, we have decided to redesign the EpiPen to make it needleless, to deal with the devastating trauma and allow for the same level of drugs to still be administered without having the issue of having the needle. And we as a team are going into our third year of redesigning the EpiPen. So we have a lot of extensive research and prototyping that has already been done. So what the goal of this year is to create a final design, get that final prototype done, really fill in all the gaps and take this project to the end. And now Casey will talk about the different aspects of epinephrine.
Yeah, so first I wanted to talk about the epinephrine. So currently the EpiPen that's used for adults contains about 0.3 milliliters of epinephrine, and this is not a lot. This is not a large amount. And comparing prices with some that's used for horses, it's very cheap. As I put there, 50 milliliters is about $40, and an EpiPen is about $300. Also depending on insurance, which is not something that's available to everyone, is around $300 for 0.3 milliliters. So this just shows the area that we can improve in for the pricing of EpiPen. However, and we also want to note that extreme heats for extended periods of time can degrade the epinephrine. So we might want to look into creating an insulation for the epinephrine to increase the shelf life and make sure that people don't have to go buy more and more. And so the epinephrine will be injected around 2 centimeters deep into the intermuscular area. If any of you have had any shots like this, it'll be administered at a 90-degree angle. Yeah, and that's about it for epinephrine. Awesome. So here's the gas cartridge. Our current plan is to use a gas cartridge to power the system. And so these gas cartridges are relatively cheap. We'll probably use an 8-gram cartridge at the moment. And this is something that none of the current epinephrine devices currently use. There are devices on the market that use gas cartridges to propel their systems. However, those are more insulin-based or basically to administer any drugs. And so currently one we're looking at is one by Leland, and it's on the table. It's the top product, the number 40106. And so with this, it's only about 1 inch long and less than half an inch in diameter. So these are very small. However, they can produce a large amount of PSI. I believe these hold about 250 to 350 PSI and have a minimum burst of 7,250 PSI. So there's certainly enough force. And the only issue here is working to make sure we can control that force. And I'll definitely go into that into our next slide. So this is our current plan is to use a relief valve. The need for this relief valve will be to ensure that we can create a constant pressure within the system in order to make sure that the plunger system that we use to actually propel the epinephrine will move at a constant rate. And this is something that's used in many systems, most commonly in air compressors. And this is something that we may want to look into ourselves to create or use an existing product, depending on the sizes and pressures available. But for a system to propel this epinephrine will be around 130 to 300 PSI. And what I have on the left is a little diagram of a simple driving force pressure valve. And in the middle, I have a little diagram of where the pressure will actually go into the system. And then once the pressure hits that X, based on the tension of that spring, which we can calibrate ourselves using a screw, the ball will actually move forward and allow pressure to leave. And on the right, I have a little bit of a diagram just to kind of walk through the steps of the pressure valve and why we'd actually need it. So in order to make sure we have a pressure constant, we want to make sure that this spring will be able to move and let out pressure as we need And this is something that we're also aware of, that because of how small this device will be, the hole that this pressure valve will be releasing from is also going to be very small. So with that, there can be a little bit of shock with patients. It'll create a pop sound. However, we'll be able to direct the flow of that CO2 so that it doesn't hurt either the administrator or the patient. And yeah, so this spring will be time dependent, and as the system moves, system ejects the epinephrine, it'll be able to maintain a constant pressure. All right, and for the nozzle, and this is the nozzle that basically, the epinephrine has to come out of, and these will be approximately 50 to 360 microns in diameter, so super small and not something we can make. So we'll definitely be buying these, and there's no need to try and design these on our own. And the requirements for the epinephrine to actually go into the body will be an exit velocity of higher than 100 meters per second. Now this can depend on the size of diameter we use. However, at the baseline, it will need to be more than 100 meters per second. And along with this nozzle, we'll be using a spacer of about 1 to 3 millimeters in order to deliver the epinephrine to the desired length, because you can't just stick the nozzle right onto the skin and have it go in. There needs to be a bit of space for the stream to actually form. And this spacer is not a major component. It's just going to be a piece of plastic that is not a major concern for us. And here we'd like to use a trigger mechanism. So as a team, we've been looking at different ways to actually actuate the system. We've looked at electrical systems using a solenoid, a more mechanical system of using the screw and a twist and untwist method. However, with the solenoid, we've been experiencing issues of finding solenoids that can actually withstand that PSI at the sizes we need. So we have strayed from that route. And as far as the more mechanical screw-based system, it can hold some issues of the need to screw in with both hands in the event that someone is trying to administer it to themselves on their own. The heavy dependence on having to use two hands caused some issues, and we ultimately landed and are currently landing onto a trigger mechanism. And this would use a lever arm so that actually puncturing the CO2 cartridge wouldn't be very hard for the patient at all. And we are also looking into having this lever arm be incorporated to other uses with the device, primarily the cap for the system, because just with this product, we want to maximize its efficiency of use. And if we can try and make this lever arm a cap, we can ensure this the cleanliness of the actual tip. But then we can also use it as a safety mechanism due to its length. It can expand the length of the device and create a safety mechanism when it's used as a cap. And also, once it's plugged in to the needle arm, we can also use it as a safety mechanism where it'll click in and actually allow the needle to penetrate the cartridge.
Awesome. So now that Casey's gone over the things that we're working on, we want to talk about our future and what we're looking at for this year of the project. Most importantly, we want to have effective communication as a team, and honing in on that final design is really important. Although we don't have the same access to 3D modeling and all of the things that we would normally have, we've kind of come up with alternative ways to still be able to create that finalized prototype by the end of this year. We have access to a budget that will allow for us to go to outside resources for 3D printing and for any other materials that we'll need. And by the end of this year, we really want to be able to have a model that can be tested and validated to ensure that it's safe and effective. So the timeline for a quarterly basis, our goal is to really have this done by the end of this year and be able to have a prototype that we can take to faculty. So fall quarter, we really want to focus on updating our members on the research and development that has been done so far, looking at old CAD models and really having good communication between old members and new members and getting them up to date on what's going on, and also investigating old literature as to what the basis of some of these numbers that Casey talks about while also doing new literature reviews to ensure that new components of our design are accurate. And by winter, we want to start that rapid prototype development process, focusing on CAD modeling and some of our new members, teaching them the basics of learning how to do SolidWorks and prototyping, tolerancing, those kinds of things. And then spring quarter, we're going to establish that final design, get our CAD model and prototype done, and have ready to present to faculty or anybody else who is interested in learning about our design. And for how many members we need, Casey and I have decided that we are really, really keen on having as many members join our team as possible. And we want to make the full team be as many people, 5 to 7 people is kind of our goal. We are looking for 1 to 2 members who can commit their full time and act as a leader of some subgroups and be kind of that person to really commit to the entire year and have as much fun with this as they can. We also are just looking for somebody maybe of this strong number to have some experience in prototyping and development and things like that. We also are just looking for anybody who's interested in biomedical engineering, especially the mechanical side of it, as we're going to be dealing with things like pressure and mechanical processes. And we are really just excited to see who's interested and who we're going to be able to get. And interviews are going to be led next week. And we would love for you guys to keep an eye out for the email regarding this. And as for team expectations, we plan on having weekly meetings to just go over this project. And we also plan on having outside project meetings and expect a kind of work put in of about 3 to 4 hours a week. This will be done somewhat on your own and somewhat collaboratively with our project meetings. It's really up to who decides to join and who we are willing to, it's going to be kind of a fluid thing, especially with COVID. And guys, I just guess kind of like come prepared, excited, ready to participate. And anybody is welcome to come. People with experience, please apply to kind of be interviewed and into the core members. But anybody with any amount of experience is completely welcome to join the team. And just come to the interview prepared and be ready to talk about your experience. And that's it. Any questions?